us today Dr. V. Chandrasekhar, distinguished professor from Colorado State University. Dr. V.K. Saraswat, member S&T at the Niti Aayog. We have Avinash Mishraji and possibly Dr. Rajnath Ram online. But we also have several very important stakeholders for a topic like this today, including the Ministry of Housing and Urban Affairs, Earth Sciences, Meteorology, ISRO, some people from DRDO, and so on. So welcome, a very warm welcome to all of you. Just let me say briefly how this lecture came about. Professor Chandrasekhar teaches at Colorado State University. As you heard, I am a graduate of Colorado State University. Incidentally, he used to be on my thesis committee also, and I was telling people that you shouldn't really hold that against him. But he has done, well, first of all, the distinguished professorship is a rare thing in all universities. So in any university, 1 in 100 full professors is a distinguished professor. So that sort of speaks to his contribution. But our meeting, a very coincidental meeting before the pandemic at Indian Institute of Science, even before I came to Niti Aayog, made me realize that his work has had so much impact on cities all around the world, and as in his own words, but has not really been taken up similarly in India, where he would really like to make a contribution, being from here. So I'm really delighted that since that conversation, he has been very keen to make that contribution. And typically when you meet people and have such conversations, they don't really take it to a meaningful conclusion, but he has been one who has stayed in touch and also have said that the next time I come, I do want to see where some things like these can find application. So what he'll talk about is again a rare instance of somebody inventing a technology and taking it to a large scale policy and systems impact. So I'm very much looking forward to this. And let me invite Dr. Saraswat to share his thoughts and then get us going.
So may I first welcome Professor Chandrasekhar to this important gathering which we have assembled for your talk today. And we are really privileged that you are here with us because knowing the background and the kind of expertise you have built in the area of weather radars and similar activities is going to be quite beneficial to all our scientists, all our stakeholders who are there. Now, I think Dr. Chintan already gave the details of Professor Chandrasekhar. I would not like to go into the details what have been given to me, but I think he certainly is from an area where he has been able to be part of the collaborative adaptive sensing program of what we call CASA. Yeah, that was the thing. He has been part of that. All of us know that radars have been used for weather prediction for many, many decades. And India has been using radars for weather prediction. The problems with the radars today is what is the fidelity and what is the kind of range and curvatures you can able to cover. The major problem which you are facing today with the weather radars is that beyond a certain Earth's curvature, you're not able to get. So the low altitude tracking of weather disturbances becomes a problem. With the global warming taking place and the kind of impact which we are facing today in terms of floods, in terms of tornadoes, in terms of cyclones, and in terms of cloud burst and all that, prediction and monitoring becomes very, very important to basically from the point of view of disaster management as well as from protecting the lives. So the new technologies which he has worked on are coming up that you can use series of miniature radars along the urban boundaries, along the hills, along the valleys, and things like that. And you will be in a position to get a much higher fidelity sensing of the weather conditions and things like that. Now, these are the areas which I think in India we are yet to start in a big way. That is my understanding. But I think the time has come, knowing that the last at least 2-3 years we have seen the impact of global warming in a big way, and vagaries of the weather have really resulted in a lot of destruction, whether it is in the Uttarakhand or it is the Himalayan region or it is in the northeast cities or Odisha. We have seen. So what we are looking for now is, with the kind of talk which we are going to get today, we should be in a position to build our own roadmap as to how we can work together with him and build this particular technology for the benefit of our weather prediction in a much more resolute manner. So that is what the purpose is. I won't go into details of this because I think the technology master is here, so he should be in a position to get more details. But I can only say that India today has got capabilities of building radars for defense applications, aerospace applications. Both Department of Defense and Department of Defense Space are well equipped for designing and developing large size radars for detection and tracking of targets. But weather radars, we have not made much headway, and we have been practically importing many of them. Some progress has been made in that area, but I think we have to accelerate that process. And I hope that today's talk takes us to a different plane. Over to Professor Chandrasekhar.
So should I go?
As you like.
I'll
Where is the slides are changed from there?
Yeah, we'll change the slides. We'll change the slides.
Oh,
Yeah, we'll change the slides. You can use the mic.
You can use the mic and you just say next, he will change it.
Yeah.
okay.
Whichever, wherever you are comfortable,
Whatever
whatever.
you're comfortable with.
Yeah.
And teacher can't sit and talk.
I know the professors have to stand.
You know, I'm a professor by trade, so it's. Can you hear me? Yes. And also from online and here. First of all, I want to say it's an honor and privilege to be invited to the highest think tank body in India to give this lecture. I'm very, very humbled and thanks everybody for inviting me. And so the context here is today I want to talk about, as when you are a young scientist, you are busy publishing papers. Then you are a mid-career scientist, then you want to run big projects. But then when you really, really mature, then you want to see the full impact. Otherwise, what you sometimes one day you think, what's the point? And fortunately, by God's grace, I have been riding this impact train fairly well. We started with development of technology, and when I went to the US, I won't say when because then you will see how really old I am. But I was fortunate to have a very strong foundation of radar education at my undergraduate in IIT Kharagpur from stalwart professors by the name Vishwanath Das, Jay Das, Sanyal,
Sanya, Chakravarti.
and big people. And then that planted the radar root in me. And then I was very lucky to be able, because before that, even in the US, that was the time they were competing with Russia for radar technology. And Russians were following dual wavelength. So we started from the beginning dual polarization technology. And that dual polarization technology today is the household name everywhere in the radar all over the world. And in US itself, it's a $4 billion acquisitions program. Next slide. So when you talk about radar, weather, and all that stuff, But if you take it one level higher, it's all about water. Water is a primordial element in life, and water. If there is too much water, it hurts us. If there is lack of water, it hurts us also. And water on the earth is not going anywhere. Only thing is, it's constantly going through a cycle. So that picture in front, it will just set up the importance of water, which is more important. And then I should bring how radars falls into this place. It's not about radars. It's all about water. And there is a whole another sector that I am working on with looking at this water cycle from space, but I will not talk about that today. So what is a water cycle? Water comes from the storms as snow and rain. And then when it comes as snow, actually it sits as, mountains hold them as reservoirs. And it's actually a natural reservoir of water that's sitting in the Himalayas. And then that slowly comes down as rivers, like River Ganges and everything. And then it goes into oceans, people use it, and then it evaporates, and then it goes into a cycle. What is happening due to climate change? This water cycle is accelerating. Whether we agree there is temperature change, this, that, or anything, this is we have documented it experimentally through satellites. And I am actually one of the PIs of the program. And so this water cycle is accelerating, which means the same amount of water is going round faster. That fundamentally explains why you see more, 100-year storms every 10 years. Because the same, it's like water in the house. You're filling the water tank, and then you're flushing, using water very readily, and then water goes away, then you have to fill the water tank again very quickly. And the water runs through the drain faster, it's flooding, and etc., etc. Let's go to the next slide. So, water cycle acceleration alone is not a problem. That is combined with urbanization. So, more than 50% of the world is now living in urban regions. And by 2030, this number will go to 5 billion. And urban growth basically concentrated in Africa and Asia. Okay? Next slide, please. And there's a lot of details there. There are two global trends. Urbanization, and instead of climate change, you can change the word to water cycle acceleration. Together is what is causing the problem. If it was just one of them, it won't be that bad. The reason it's bad is because these two things are hitting each other simultaneously. Next slide, please. So, there is a lot of snippets. The urban population will exceed 6 billion. In fact, 2 days ago, there was a huge article in Indian newspapers about urbanization and water. And managing urban regions is where, I think somebody has put out, I don't know, it was in newspaper 2 days ago. They say that's where investment, this is especially for India, I read in newspapers, that investment in India is needed for excess of $100 billion. That's what I saw the number quoted. And it was specifically referring to water. Next slide, please. Because water is primordial element in life. And the basic interaction between precipitation and surface runoff and geography, etc., and then global annual precipitation is on the rise. So the human factor plays a big role in it's intensifying water cycle will result in increased storm density, and all the water will suddenly come in 1 or 2 storms, and we need that water. Let's keep going. Next slide. That's the main statement here. Water is at the heart of both the causes and the impact of climate change. So, it's water. Next slide. And it's unforgiving all over the world. Left side is a picture from Mumbai, and in the middle is from Beijing, where they have got all the money in the world, but still it's an issue, and we have to manage that. And then the right side is Louisiana and New Orleans. It's a low-lying city. Okay, so what's the problem with water? Because a lot of the water infrastructure that's developed today is based on some design equations saying that so much rain and so much water is going to come. And for many times people have seen that in the southern part of Europe it rains a lot. Accidentally one day that type of rain happens in England, it just creates havoc. That type of rain is called Tuesday in Mumbai and so on. Next slide please. So right now the radars that are deployed, they are part of national infrastructure, and it is at a national level, but because the same radar was also looked at, seen as aviation safety, terminal operations, it's trying to do too much. And energy management and then smart city infrastructure. But all these are, if you go look at these radars, they will never get permits. If you want to go put one of those radars in the city, nobody will ever get permission to put those radars. They are too big, military industrial complex radars. They are not the little ones. Next slide. So this is the US National Weather Service infrastructure. There are about 160 operational radars. There's a lot of details. Let's skip this. But these are what is called as, that's the next thing I want to bring in. The radars actually came in too early before all the innovation in data and IT came along. So today's weather radars are actually data push networks. They just go round and round and round. All radars operate the same way. It doesn't matter, and then it just throws the data over the fence. Okay, you go figure it out. But what we need is, next slide. The new systems, we need data pull systems. When you have storms coming over Chennai from a cyclonic storm, or if you have another storm that's interrupting the convective storms that are taking over from an airport, we need those radars to be operating differently. Next slide. So I wanted to give a little bit of entertainment here, because a news person will tell the story better than a professor. So, is the audio coming through this? Let me see.
From ABC News headquarters, this is World News with Charles Gibson.
The National Weather Service now says the severe storm yesterday that killed one person and damaged more than 100 homes in New Hampshire was a tornado. This has been an especially violent tornado season with 120 deaths, nearly twice the number in an average year. The toll could be reduced by giving more advance warning of tornadoes. A revolutionary new radar system promises to do just that. Here's ABC's Ned Potter.
No matter where the storm strikes,
it's a tornado.
People say the same thing. If only they had had the slightest idea.
It was so fast, it wasn't even 5 minutes.
It happened again yesterday with the storm in New Hampshire. The U.S. has the most powerful radar network in the world, called NEXRAD. But even so, the average tornado warning comes only 12 minutes in advance. And 3/4 of the warnings are false alarms.
So please note
which is
that
why
3/4
researchers are working
false
on the
alarms.
next generation of tornado warning technology.
So people
They
don't
call
trust
it
them.
CASA, small high-tech radar like this one in Oklahoma that can be mounted atop buildings or even cell towers. Combined with powerful computers, they should eventually be able to tell you whether your street will be in danger, something NEXRAD cannot now do.
NEXRAD is so powerful that this antenna can see for 250 miles. But it can only see in a straight line, and remember, the Earth is curved. So there may be a funnel cloud 50 miles away, but this antenna cannot see whether it's touching the ground.
But because Casa is so much smaller, you can dot the country with as many as you need, filling in the empty spaces between NexRad domes. And since they'll be closer to the action, they can see much more detail. Here's a NexRad scan of a storm front moving through Oklahoma, and here's the same thing seen by Casa. The old NexRad, the new Casa.
Tornado on the ground.
So you can skip.
In future years, new...
So the thing is, we got to make large number of small radars. And in the old days, if I, even 15 years ago or 10 years ago, if I came and gave a talk like this, radars are too expensive, this, that, everybody will say that. But anybody who's got a modern car, all the modern cars have radars now. They have radars that run at 75 gigahertz frequency, and manufacturing has shown how to bring down the price. So when you get into these small radars as opposed to big radars, and then you make it in large quantities, and then you put so many number of radars, it's not just about radars, it's about IT. Because it's information that's important. People say, don't give me data, give me information. But then also the earth curvature is a big issue, because a lot of the radar technology that's used in civilian sector is what we call as hand-me-down technology. Because military sector has figured out the technology of radars, and then that's taken and then used directly without, many times it will be given for free and then it's just used. So that's part of the problem. And so it has to be, the whole system aspect of this has to be rethought, as opposed to just purely technology. So when we have a whole solution to a problem, it has three fundamental planes. I will get to that when I have a slide on that. Second thing is, and many of you fly these days compared to the time when I left India. Nobody flew, everybody took trains. And suddenly there will be a ting sound, and then everybody will say, please put on your seat belts. That happens when the airplane crosses 10,000 feet. So when the radar coverage for the US was figured out, it was based on 10,000 feet coverage, because that level of thinking comes from aviation and military technology. But last time we checked, there are not many people, except you go to the Himalayas, people are living at 10,000 feet. Everybody is living way below. So if you put, for example, 1 kilometer or 3,000 feet, see the diagram below is the coverage of the US. Most of the US is not covered. And especially, see the west, where Colorado is, that's not covered. And that's because the west is mountain regions that produces immediate flash flood producing storms, and then it creates flash floods. It's just like the type of floods that you have seen in Uttarakhand, and it happens in complex terrain. It has happened in Colorado. There is a big flood called the Big Thompson flood, and in those days people tried to outrun the storms with their cars. Raging waters came and just caught up with them and then killed so many people. So this day and age, if we know a high value asset, there is no reason to, you can just put radars in the mountain valleys to give advanced warning. But that's a different story. And I'm actually doing a project right now in Colorado mountain valleys to demonstrate experimentally about the impact of this water on snow water accumulation, because that's another thing that's being affected right now is the quantity of snowfall that's going into the mountains. People may ignore that because that's not where people live, but that's the source of water coming down. So that's something we need to keep our eye on going into the future. Let's go to the next slide. Let's skip this. So there is a lot of National Academy reports that I've looked into this. I served on some of these committees myself. Let's go on. Next slide. Okay, this is all research. Then government told us, go show, put it in some city and show this will work. this will work in societal aspect, plus it's economically feasible. That is, if we want to put radar network in a small city, see if this can be managed with the city itself, except the broader city. Dallas-Fort Worth is like a big metroplex. This is almost the fourth largest, and we picked Dallas-Fort Worth because it has the biggest impact with floods and different types of storms, and then that city has 2 airports. So you can take Dallas-Fort Worth and then replace it with one of the big 4 cities in India, Chennai, Calcutta, and Delhi and Bombay. And the area, population, everything will fit out. So each of these circle is these small radars that we have made. And then we put 7 of these radars over the city. And the main thing I wanted to show is these small radars can ride the existing infrastructure in the city. That is, you don't need to go buy land and you don't need to build a big tower. All these things is impossible in cities. And I was advising Korean government people on putting some radar. And I kept talking about this radar is cheaper, that radar is cheaper. They were like ignoring me. I said, I get this feeling I'm being ignored. I told them, yeah, but we don't care. The cost of civil works and the real estate prices 10 times the cost of the radars. Radar cost is trivial in this whole project. Because a lot of the times when we think about radar technology, we are so obsessed with radars, we forget about everything else. That alone is going to make these radars acceptable. So I wanted to show pictures of how these radars are being deployed. Next slide. See, that radar, one of the diagrams, you can see it is being carried in a helicopter. So it's not very heavy. And then you can take a small crane and put it on the rooftop of a building. It almost looks like a water tank. These are different radars being deployed in the city itself, in Dallas-Fort Worth. And let's go on. So here is the big picture that because this picture diagram I brought specially in honor of this Niti Aayog discussion. There are 3 planes in these big programs. This actually program was we developed as part of our big National Science Foundation program, where whenever we develop a completely transformational technology. Before this project came, nobody believed that these small radars would ever be useful. First of all, there was a belief that X-band doesn't work for weather. So we had to develop technology for weather using X-band. For people who are not radar geeks, don't worry about it, it's another frequency. And the frequency in your microwave oven is S-band. If you open the door, microwave oven and look at the door, the frequency will be written, and 2.4 gigahertz. But this is much higher, this is 10 gigahertz. And get into this almost like 5G type spectral bands. So you have basic science. So I work with people in atmospheric sciences. They actually study the raindrops and then convince themselves how you can actually get quantitatively rainfall rate from these radar signals. That's basic science part of it. But then the middle plane is technology. Then we have to build the right kind of technology, that is radars, instruments, materials, so that it will all work. But the most important thing is the top part, which is system, where everything has to come together and the end users are living in the system. If we can build the best technology, and then if we have very good science, but if it's not turning it into a useful system, we just have to write papers and then go on to things. Nobody will read our papers, and it doesn't turn into anything. It won't be a national infrastructure or an urban infrastructure. The next point I want to make is, if we go around different countries, whenever a radar allocation is made, that is typically associated with some approval in the national parliament. That's how big the budgets were. But these small radars, now they are much less expensive. They can fit in city budgets and state government budgets. That's another very important thing. So that's the reason why we went. So we needed to also show the economic model of implementation and the routine maintenance would work. And plus, if the city people are going to pay, I have to go convince the Council of Governments in Dallas Fort Worth, this is good for you. This will be useful. So I had to do a sales job, and I'm a professor. I'm not the best salesperson, but nevertheless, it worked. So this is the three. For a big program to be successful, we need all three planes to be spinning at the right rate. If you just build a system that it's not supported by very good technology, there will be too many failures and nothing will work. It is like you build the best sewage system in the city for water and then everything gets clogged and we don't put in the right kind of filtration system. Or, there are so many examples I can give. And sometimes the basic science itself fades, and so on. This three-plane diagram is what we find out. We almost worship this diagram every day before make these big programs work. My definition of big program is $50 to $100 million program. Then we need to have verticals in all three planes. Thank you. Next slide. So I see I did some homework on. I didn't recycle the slide. So there is one more thing which is about atmosphere and water. In the old days, we had a lot of observations. India actually has a historical culture of rain gauge observations. But our models were not really good. But there has been an explosion in computers. Now models are running way ahead of observations. That's another reason we need to be making observations at a much better resolution. Next slide. Next slide. So I just wanted to tell you, all this is not a very simple thing. This is all built out of very good basic technology. I'm going to skip this because I just wanted to show a glimpse of the basic science and technology that's here. But since this is more of a policy talk, and so I'm going to skip these slides. Let's skip this. But I want to keep these slides.
No, you can cover some. I think there are some radar people that can be.
Okay, let's go back. Yeah. So the axis spin that works on all these radars is basically dual polarization technology. And let's go to the next slide. So the electric field is a vector, and then it has the direction of electric fields actually describes the polarization. By making measurements of two polarizations, you essentially characterize the non-sphericity of the precipitation particles in the atmosphere. That really is what makes it successful to make the distinction between water, ice, and quantification of the amount of water. So basically, we have very accurate rain gauge and at a very high update rate that I'll show you examples. So that's fundamentally enabled by this technology, which was pretty much invented at Colorado State University. Of course, you started the research, but many other universities joined eventually. Next slide. Next, let's skip this. So typically the way it works is you send one polarization and you receive the same polarization. And then you click again, then you transmit the vertical polarization and receive vertical polarization. And this of course, is useful in military, but this is the fundamental axis spin of every modern weather radar technology. And because it helps in so many things, elimination of clutter, and it's got like 85 things it's useful for. So it's very, very, very basic. Next slide. Okay, this is important. You will see, we talk a lot about radars, and if there are radar scientists, the old days, we just buy radar and forget about it. But radar is probably 1/5 or 1/6 of the story. We need to work with user needs. So you have a bunch of radars, but then it's all about data. Next slide. You need to keep clicking. And so you have data mining, and then optimization of operation, dissemination of products to users. All this is now makes the whole system very versatile. And we made all these things work. Next slide. But keep going. Now click. It'll keep clicking. But that's inner loop, and this is the outer loop. It's not important to make the best observation. How do we get the best response from people and users? That's more important. Let's go back one slide. So this concept of building technology inside people was actually invented in MIT. It's called the Kleos process. And you've heard of Kleos.
Jerry Sussman's. Joseph Sussman.
I know. So now I've graduated many people working on the Kleos process. So how to include people, because people are not designed by law of physics. Their response is very different, and I can start on that and then we can go on and on. But nevertheless, we have to include people in this response, because especially when it's connected to water, that's very important. And next slide. So the best way to see if people believe in this is Japanese were the first ones to adopt this. So their thing was any city that has a population of excess of 10 million. So what they did was they put in the city X-band radar network, and then that drove the technology. Many of the industries started spinning up X-band manufacturing, and I myself was involved in advising and implementing this. There is this Disaster Mitigation Institute in Tokyo that I used to visit regularly. It was in Tsukuba, and so with that, many radars were deployed. Next slide. So I don't have to get into this. Then there is this Seoul and Busan went ahead for this urban radar network. And then the next thing is there's numerous examples in China. They're just cranking out X-band radars and small radars like there's no tomorrow. Next slide. So I wanted to show instantaneous rainfall products that you can put out in the city of Dallas-Fort Worth. That's if you can't read, there is a clock updating inside. It's every minute. You can see it. There is a lot of AI, artificial intelligence, that's being used with these days to do precise city and street level monitoring and forecast to evacuate people very effectively. Next slide. Let's skip this, and then let's skip this also. I'm just saying it all works. Okay. So that's what do you call it? Shovel ready to implement. So what am I doing next? I talked a lot about water and the importance of water, and then water being primordial element. So the next thing I'm going to show is a new project, again, large project I'm working on, which is more focused on water and shortage of water. So this is a joint program that I'm doing with NOAA, which is National Oceanic and Atmospheric Administration. And this is again, so I talked a lot about urban, but now I am slowly expanding to regional, because sometimes urban boundaries don't end at one place. If you start building some urban activity for city of Mumbai, where does Mumbai end? Very quickly it becomes a region. And so we started working with this in San Francisco. Then there is San Jose. which is as important as San Francisco. And then you go a little bit to the north, there is Santa Rosa, which is the wine growing region. Everybody says, no, we need to be in the show. But these are all, we're not talking about thousands of kilometers away, like going from one state to another. Within a state where the urban regions are suddenly becoming too big. So then it's not like, what do you call that? Mumbai's water is as important as Kalyan's water or Thane's water, because they're all Mumbai, depending on who's calling what as Mumbai. And some people say, are you living in Mumbai? They say, no, I'm in Thane. But then when water and flooding comes, it's all the same. So then we started brainstorming and then started doing this. Next slide. Okay, we have to stop here. This is almost, I can take this slide and change California into Chennai and Tamil Nadu. A lot of the precipitation comes in a handful of storms, big storms that bring water into, we have a scientific secretary, I'm sure he knows that. There are 3 or 4 big storms that bring all the water for Chennai. If those 3 or 4 storms become one storm, there is a water shortage. And if 3 storms become 6 storms, there is massive flooding. And same thing happens in California. So it's like, we call it atmospheric rivers, a whole stream of water that comes and then dumps all the water into rain. And this is very vital for replenishing water supply. But the atmospheric rivers cause a lot of flooding. And they are responsible for more than 80% of the flood damage in the western US. And actually we have costed it out. It's more than $1 billion in annual damage costs. That's only one part of the story. And it's San Francisco Bay Area is very vulnerable because if we are not able to manage the water and if the sewer water runs in and then goes into the ocean, then you have all the problem with fisheries. And then if this happens with the high tide, then we need to bring the coastal models also into this big picture. So this sea level rise, urbanization, the uncertainty of atmospheric rivers, they all say that we need, it's like everything else. Suddenly you have mosquitoes, we just have to get mosquito nets. We can't just say, oh my God, there's climate change, we can't do anything. So this is something similar to that. Next slide. So we want to meet the challenge, so we proposed and then prepared this project. It's called, we have to change the name, it's called Advanced Quantitative Precipitation Information System because we wanted to make it all about the vertical with water, this project. And then we wanted to integrate the capabilities of, here we spent more time integrating the users and then wanted to spend time on flood mitigation, wastewater management and freshwater management, water quality, emergency management and transportation. Transportation is one of the first ones that get hit due to flooding. There is no better example than city of Bombay, Mumbai. There is every time there is a big monsoon excess, first thing they show is all this trains standing in water. So it was supposed to be a 4-year project, but it's still continuing. And once the project is more complete, I normally come out and give presentations like this. It's fairly mature now. But there has been a significant delay because of, everybody knows why. You can guess why? COVID. Yes. Nowadays in this world, everything we can blame on COVID. So.
We got so much used to it now. Every meeting I hear COVID.
So, next slide please. So I just wanted to show you, we built a lot of partnerships with this. You can see we are the scientific and technical arm that oversees the project. NOAA is a major partner. It's actually NOAA and Colorado State through our NOAA Institute at CSU are major partners of this program. And then Scripps Institute of Oceanography, US Geological Survey, and the left side is all local users. The right side is big system users. Next slide. So these are the components, and because the X-band systems have been shown, we brought in some C-band radars because we wanted to look into the ocean and then get into this atmospheric river programs. So 1 or 2 C-band radar umbrella along with the X-band network in the urban region is there. And then also we built integration of observations into NOAA's models. And then precipitation, stream flow, and coastal storm surge, that was integrated into the system. You can see there is a lot of IT here. IT is so important in this project, and then when IT comes, you bring all this information, then there is so much activity of AI. I don't want to go into a lot of that. I wanted to talk about the big project and then the system integration. That is because this is I'm not giving this talk in one of the IITs, I'm giving this talk in Niti Aayog, so I wanted to talk about the system. Next slide, please. This is the system and how things are integrated. And then, next slide. That's the layout of the radars. As we speak, a lot of the radars are being deployed. And I'm sorry you cannot read the details. The big red circle is the C-band radar. And then you can see that whole area is Bay Area. Everything from Facebook to Apple to Google to everybody, Intel, HP, everybody is there. It's a very high value asset area. And then in the north is the Napa Valley, the wine capital of the US. So there's a lot of agricultural impact, and below is high tech. And that region, when you come further down south, it's very arid region, so water quality and water quantity is important. Next slide. This is some systems being deployed and then evaluation of products. Next slide. So here's some data examples of the traditional long-range national scale radar. Whereas on the left side is the high-resolution local network, and you can already see the local people are really enjoying this improvement. And you can see the high-resolution precipitation. And both animations are running in same time, which means what you can see is on the left is the update time is much faster compared to the right. When there is raging floods, today, including the US and as I'm sure it's in India, the update time for national scale radars is 5 minutes of the order. If you have raging waters going by, you tell somebody, you'll get your next update in 5 minutes. If you want to know how long 5 minutes is, many of you have microwave ovens. You put something there to heat for 45 seconds and stand next to it. That's the slowest 45 seconds you have seen, right? You're agreeing, right? When you're waiting for something, 45 seconds to 60 seconds is one of the slowest times. Not especially when you have raging floodwaters. Next slide. In fact, because of this, so many people can take videos. It's very sad. I've seen so many raging mountain rivers in Himalayas washing people away with water, and they would be taking videos for just 1 minute, and it's really sad. Go back. So this is another thing. There is a whole other dimension that I don't want to get into right now, which is as important for India, is monitoring the mountain regions. And we do have this mountain region monitoring. especially is there an impact on the snowfall accumulation and snowfall rate? Because there is a lot of talk about the snow deposition and the glacier behavior changing in the Himalayas as well as in many parts of the world that directly impacts water. Availability of water, because water won't stay there for too long, and then a lot of the snow directly sublimates into vapor instead of melting and flowing down in rivers. That issue is being addressed right now, but that's a current project. We'll talk about it maybe in the future. Next slide. Let's skip this as I'm just showing. So, what is this? This AQPI is a prototype for monitoring precipitation, stream flow, and storm surge, but it's all about water and water vertical with smart cities. And whereas the previous project I talked about in Dallas-Fort Worth it's all about storms and smart cities and the impact of storms. In fact, Japan, the main ministry that took up this project was Ministry of Transportation. It's not Ministry of Weather. The Ministry of Transportation is the one that supported these radars, primarily to take care of the transportation sector. And the impact on transportation sector in very high density populated Japan was much higher than their water problem. They don't have a water problem. What they have is excess water. And in fact, I have been to some of their storm storage systems. It's unbelievably huge. So this also gets into this NOAA's Weather Ready Nation initiative, because of all the climate change, we have to be weather ready, and then to support impact-based decision support, but more at a local scale. So I really expect and foresee this project also is the business model of this is NOAA plays an advisory role, but this is a regional project supported locally, financially. So I think what I need to do is I have talked in general about the various initiatives and then the verticals, the business model and the system. And I think that maybe, let's skip slides, keep going. Keep going, keep going, keep going, keep going. But I have some, I should have put the thank you slide first. Yes.
All right.
Dhanyavad.
Thank you so much.
Now I want to open it up for questions, and I hope I see very familiar names on the internet, and I don't know if, anyway.
I can open us.
Please.
With a question. So, by the way, this is a beautiful example of Clios that you
Yes.
gave, and for everybody's benefit, the Clios is an acronym for Complex, Large-Scale, Integrated, Open System, I think. So the way this came about, I mean, like to me, the idea of you creating this consortium of a variety of stakeholders who ought to be involved is fascinating. My question is more about the organizational form. So, there used to be a gentleman here, Dr. Shekhar Bono, until recently, and we used to discuss this question sometimes in the evenings over cups of tea, that the challenge in organizational design when you have such implementations, large scale, right, is that you are trying to deliver something over a long term. But in many organizational settings, such as this one, it may be through short-term tenures of people, for example, right? So here in the Dallas project, how long did it take, for instance?
So we were able to spin up at some level at within 3 years.
Within 3
And
years.
the thing is, once the thing is, all these projects, you can't say that we are going to do this, we're going to do this. People lose patience.
Yeah.
And it's like putting out this new metro.
Yeah.
If it takes 5 years, when people have to put up with traffic, then they lose patience.
Yeah.
So within 3 years, we had to show something, but it's not a complete system.
Yeah. So I think
And then what happens is, we also had a lot of turnover of people, and the only constant in the whole thing was me.
I see. So I was going to ask you that question, that who was the constant? Because we were thinking that, either you, like Shekhar and I were thinking, either you do everything as the government anchors it completely, or some actor in private sector anchors it completely, or it's a combination of the two in the design of such projects. If it is a combination, then the question is how government heavy it should be versus, So what was it here?
So I am what you call semi-government. So I don't run this. You don't say university is running this project. People lose respect, because university is supposed to be doing things at its own pace, doing research and writing papers. So we operate through what is called, we have a cooperative institute of NOVA, which is inside the university, but it's meant for managing these large projects like this. It's called the CIRA. So I run this project through CIRA. And I'm talking about the California project. And whereas with the other Dallas-Fort Worth project, National Science Foundation set up the structure, how it should be done. So parallel to me, for the other project, I had a lady named Brenda Phillips. She's MBA from Yale. So she manages people in the business, and my job was to make sure the whole thing works. And in the other one, so I have a NOVA counterpart. And then they actually took one of the local districts, and the project management was done by them. They used to manage us. But it's like a very interesting matrix structure. Myself and this gentleman from NOVA were in charge of the project. But the project management is done by somebody else in California. And it's assigned by state of California, and then we had a reporting authority who would evaluate project progress. Though we are on the top. It's a very interesting management structure. But because these units were in place, we have seen examples of in those subunits, there have been turnover of people, but the next person took over and just continued. So it is made, immune to people changing.
Yeah, possibly because of the project management unit also that keeps track of that history and continuity and all of that. And I think India has found out one such structure in things like Aadhaar, UPI, now ONDC, where there's a private component and there's the government component. And I think that combination has delivered something very interesting. But that organizational form is still a very important question for such large.
So this is supposed to be, again, now I'm going to throw a second name similar to Cleo's. This is the triple helix success story, which is academia, industry, and government. And this people talk about this as a triple helix example. I've actually taken the same thing in Helsinki and implemented this for the city of Helsinki with industry, and then Finnish Meteorological Institute. And I have a professor appointment at those visiting professor appointments. So I sit on building these projects. And there, it's 100% climate change.
This satellite data, whether it is not of use, because you see the storm and the precipitation, this is because of the result of the cloud movement. So
unfortunately,
for instance, NOAA is getting the data on 15 minutes interval. And not only NOAA, but even there are many, and the data is available in open access. Then why need I to go for the radars?
That's what I'm...
Maybe go for US.
No, in fact, the
Because
point there is that basically.
The thing is, the one thing you yourself said 15 minutes.
Yes, 15
But
minutes.
15 minutes is not enough
Maybe-
to see
maybe
flooding.
true, maybe
That's
true.
the first point.
Yeah.
Second point is, as of today, none of these satellites can measure rainfall.
No. For rainfall measurements, we have got, for instance, in India, the rain gauge stations.
Sorry?
They are all rain gauge stations. They are all telemetry connected, and all Mic 2 and all those software, maybe some upgraded software, they are all running. And our prediction rate is 98 to 99%, and that is some 24 hours or even 36 hours in advance. So let me know why the India should.
Well, all that I can say is, if you think your prediction you're making with the gauges is sufficient, then we have nothing new to offer.
Flooding which you have shown for Bombay and all other cities, that's because of the drainage problem. The drainage congestion and urban settlement which has come up in the drainage lines, but not exactly. Yes, it can be true for the geography of US because it is being hit so regularly by typhoon, by cyclones and all. But I don't.
Typhoon and cyclone you can
And
predict
we-
well in advance.
Our coastal area like Odisha and all, they are managing very well. We are not getting
No,
impacted
if
so
you-
much with this.
If you think you're managing very well, then we don't need anything then.
M1 cyclone which has hit, and the loss of life was just 2 and not much property. I don't feel it has got any relevance.
I think,
That's okay.
I think you have to give one clarification. The group of radars which are, cluster of radars which are deployed for low altitude near boundary measurements, I will call them low altitude lower boundary measurements. And you also showed in one case a large C-band radar being put. Obviously, there is an integration of information which comes from those large radars or satellites as well as this cluster, which has to be data managed together to make predictions.
And sir,
And I am trying to endorse the views that these low altitude radars will be giving you much better idea about the rainfall compared to the rain gauge. Rain gauge measures after it has happened. Whereas what radar will give you is the impression as soon as the cloud formation takes place.
15 minutes.
Cloud formation based upon the densities, it will be able to tell you what exactly is going to be the rainfall drop size. In fact, IIT Hyderabad has recently a project we are doing today for actually predicting from the cloud directly and measuring how the cloud will result into ligament into raindrop, and what will be the density of the rain that will come, using a similar concept. So I think this is what is happening in this case. You can clarify that.
No, but my goal here is to, in US, their radar resolution is 5 minutes, and they find it's not enough. So if you say I have 15-minute resolution, and if it's enough, I don't know how
Yes,
I
sir,
can.
exactly. I agree with you, Chandra sir. Especially the cloud burst kind of things will happen within 15 to 20 minutes. You will get a downpour of lot of rain. So if you have Chandra sir rightly told, with 5 minutes is not enough for a cloud burst kind of thing. Everything over in a 20 minutes, we have to have at least 4 to 5 observations. So we have to take at least every 3 minutes interval. For a town burst, nowadays IMD is telling that this is the event we cannot cover.
Rain gauge or satellite. That's why radar.
So another thing is satellites
So we have about
cannot
60,
measure rainfall.
we have about 60 smart cities who have joined. So that's one.
Oh,
Yeah. We also have a question. So Balaji Narsimhan, if you can unmute and ask a question.
Okay. Thank you very much. Very good evening to all of you, and thank you, Professor Chandra, for that wonderful lecture. And I just want to give an example regarding the 2015 rainfall event that happened in Chennai. There was quite a bit of variation in the rainfall that we have received, and the catchment being small. And I think, when we were looking at some of the satellite-based, products as well as our Doppler-based S-band radar products, we could see quite a lot of bands that were not even captured by the sparsely located engage data. I think we will be able to for mega cities and things like that. I think radar is something that will be extremely useful, and I think that's the way to go. And then I think this also will play a major role in terms of nowcasting and things like that. Where it will be very useful for not only for flood forecasting but also for transportation sector. So I think what you are proposing in terms of expand and things like that is something that will be very useful. Another problem with many of the rain gauges are all, somehow during these heavy rainfall events, sometimes you don't get the signals, sometimes clogging happens. A lot of maintenance issues also happens with a lot of these rain gauges. So I think there has to be a good mix of radars, expand radars, as well as high quality rain gauges that are well distributed is something that needs to be the order of the day. Thank you very much.
Okay,
Thanks for the wonderful lecture. Thank you.
I will take your comment as thread to make two profound points. And first thing is, actually this question was asked to me by people. We measure length. We've been measuring length for a long time. The problem is solved. There is a standard for length in Paris. Everybody fits to that standard. You measure 1 meter, that's 1 meter, story is over. Measure weight. Somebody has put a standard in Paris, it's over. You look at measuring rainfall. 5,000 years ago, our kings tried measuring rainfall. You go to Korea, 300 BC, there were Korean kings trying to measure rainfall. Now, NOAA, JAXA, everybody is still trying to measure rainfall, and it's one of the most difficult problems. Why? Because it's not a solved problem. The reason is rainfall has variability at all scales. It has variability at a global scale, regional scale, local scale, and rainfall is not a homogeneous field. Rainfall as a field goes from microscopic to macroscopic. It's not falling water in a waterfall. Rainfall is made of individual raindrops. That's microscopic. That's the reason why it is not been measured successfully. So I used Balaji's thread. He mentioned about all the variabilities. That's the first thing. Second thing, if you want to change, so Koreans have tried this. They put one rain gauge every half square kilometer, the densest network in the world. So I was in Dallas-Fort Worth, and then one of the cities, I won't mention names, one of the cities in Dallas-Fort Worth, they had so much money. What did they do? Went and bought a lot of rain gauges. So they put a lot of rain gauges, and then we put our radar, and then we compared. Our radars these are independent radars. They don't adjust the rainfall with respect to gauges. So the gauges and the radars didn't agree. So then they told us, okay, then adjust your radar rainfall to match the gauges. I said, yeah, I'll look, but I have to find something off in the radar to make that adjustment. So I sent our people to they worked very hard. They couldn't find anything to adjust. I said, sorry, unless I find something to adjust, I cannot adjust. So what they did was, then somebody saw me very stressed in my face in meetings. So there is a nearby town, another town, where the gauges are deployed and maintained very well. And the cost of deploying and maintaining a gauge extremely well is very, very high because there is human cost involved. Many people deploy a network of gauges and then telemeter everything and then blindly believe them. So it turned out this is next city. It's like Noida versus Capital Region or something. It's just next to each other. There, the rain gauge and the radar agreed perfectly. It's the same rain. In one city it agrees, the other city it doesn't agree. What does it mean? The gauges are not being maintained well. there are so many gauges, and the cost of maintaining gauge network is way higher than individually if you increase the cost. So the bottom line is then they send people, the gauges were deployed some time ago, some places the tree has grown over them, some places that gauge itself is tilted, and then there are so many gauges. So from that point, what they did was when there is a gauge and radar mismatch, they send people to check on the gauges. It's come the reverse. So it is where there are a lot of people have experience. Gauge management is a huge problem and it's not reliable. But I didn't want to argue publicly against you. And sometimes gauges are misled at many places because the streams have more water than the amount of water seen by gauges.
This technique which you have used, it has helped geospatial collaboration. You are doing that in this case?
Sorry?
That means you are deploying, say, 10 radars over an area of, say, 10 square kilometers or something. Time synchronization and spatial synchronization.
Yes, it's all.
Time management, time study,
Yes,
because
everything is now disciplined with GPS.
GPS integrated.
So those are the 2 points, the gauge issue that Balaji talked about, and then he's a practicing hydrologist.
So we have one more question.
Yes.
Thank you, Balaji, for that question. Ms. Govindam, you can unmute yourself and ask your question.
Yeah, thank you. Thank you, and thank you very much, Professor Chandra, for an interesting talk. I have one question that the proposed AQPI, which is Advanced Quantitative Precipitation Information. So how is only the radar rainfall estimate, and what else has been added to this AQPI, which is, I think I could not get very clearly.
Yeah, I went through that fast because it's a current project. There is coastal model, and then there is surface flood model, and then in the city hydraulics modeling, to support flooding. And then it also, the data is fitted into this high resolution rapid refresh model for NOAA. So everything is put together in this.
Okay, thank you. Yeah, I just
so
want
I
to
had it in one of the slides, but I ran through it fast.
Okay, I just want to update this forum that it's our project for Mumbai. So we are working on it, and this next monsoon, we hope to have this network of 4 radars in Mumbai metropolitan region. So we also faced a lot of difficulties in maintaining the gauge network because the gauge sites where some of them were schools in COVID, it became COVID centers, and it's difficult to maintain all the rain gauges in our radar network could be set up in this coming monsoon. So we will update further, and we will look forward to your constant interactions and collaborations with you. Thank you, Professor.
I want to make a general observation in this case. Whether it is rain gauge or radar, and an equipment is as good as it is manned and managed. So you can't say that rain gauge is bad. Rain gauge is bad because it's not properly maintained. Similarly, radar also could become bad. One day the radar power comes down suddenly and you are in trouble because the amplifier has certainly gone into trouble. So it's a maintenance should not be considered as one of the criteria for this kind of a thing. I agree with you that there is a instrument for doing this, but radar is a better instrument for doing that. There is no doubt about it. So that is a message I think the speaker is giving us today, and we have to take it in that way. It is a much better way of doing it.
So I'll just like to add also.
Yeah.
And is also having a network of radars, expanded radars for the northwest areas. So for Himachal, Uttarakhand, so we have placed about 10 radars are being installed, so that we can have.
So in fact, that was my question, and which has been given to me also. In the Himalayan region, particularly, we see a lot of disastrous activities in Uttarakhand, Himachal region,
Flash flood.
and flash flood, things like that. What is your recommendation that in the Himalayan region, can we have deployment of this kind of radars, and how will it be effective? What kind of a project you would recommend?
So it's such a heartbreaking story for me because when the Uttarakhand flood happened, I got so many phone calls. you work in this area, and then this is actually when I built this small radar network concept, I kept telling about mountain flash flooding as a popular case. So people are used to listening to me and saying this. Why you talk about this all the time? How couldn't you get this done in India like this? So it's like they think as if I just go one day and then I can build a network. But it is a heartbreaking story. So main thing is, obviously, it's impractical to flood the whole Himalayas with expanded network. It's not possible. Having said that, so just for that, we are ourselves, and I have a network in Colorado and the mountain valleys. We have to identify a few high value or highly vulnerable asset areas, and I can come and help design radar placement and infrastructure. And in fact, I have written a new book in which I have given this as a homework problem. The book is to be released next year on the weather radar, and then things like famous pilgrimage places like Badrinath, Kedarnath, and all these places. I think they can associate a network radar deployment. Some of them just 3 radars would do. And then I've actually come up with procedures of how to. The operational issues of radars in the mountain is very different from operating them in Bombay.
I know, I have seen the military operations of the radars. If they are put in some very high altitudes and all that, in valleys, they have a problem of maintaining them.
The main problem is clutter.
Clutter, the huge clutter comes.
And then clutter mitigation, and that the problem is
multipath and clutter is the main problem in valleys and hills.
And then so we have developed an operational scan strategy for these radars, and then so it'll be good to have. I do have a mountain prototype that I didn't talk about today.
Do we have a geographical map of vulnerable points as far as the Himalayan region is concerned? Because these are the hot spots which are responsible for high intensity rainfall. Or after all, Himalaya controls a lot of weather pattern in our country. So if we have done based upon statistics, then we can indicate that these are the hot regions where we need to make measurements.
Digital elevation model is also available right now. And so if we find, because it has to be driven by vulnerability index.
Absolutely.
Actually, if you go back and see one of my slides, the main design factor in that Panditray asked, and Dallas Fort Worth, the city, everybody is vulnerable. Whereas in the Bay Area, we put in a vulnerability index. And based on that, we came up with the radar deployment. And plus, there was a second factor involved, which is who is willing to pay for the radar.
No, sometimes we need to queue. Sometimes even these radars will need a queue. And for that queue, you can use, like he has used that large radar, or probably even you can use other high S-band radars and things like that. So from one frequency to the another frequency, you can always have a correlation.
So one is the hotspot, but against you haven't changed the range pattern is also changing.
That's one of the main reasons why we need the radars.
We need radar for that.
Because you can watch them happening, you can see the microphysics, you can see the ice-water composition, and during the storm, now you've turned on the microphysics in me, during the storm you can watch the change of the melting layer and everything you can see. And the thing everybody is wondering and worrying is if the microphysical behavior itself is changing because of climate change. That, unless we watch, we wouldn't know. And so I saw that Uttarakhand area again and again, the same place is being hit.
I think we'll work on that. Please, sir.
No, just I want to curiosity whether all the radars data it is assimilated into the model.
Okay, there are models and there are models and there are models.
I'm talking about atmospheric model.
So there are 3 levels of models. So everything is a scale issue. So a high resolution rapid refresh model, we are assimilating them into this to show the impact at short term. But then we need to jumpstart the models at different scales. And then there is nowcasting models, And then, so there is various level of assimilation of these models.
Nowcast
In the AQPI,
Nowcast you can give from the radar.
no, but now we are doing nowcast with the radar and model also combined. I have some papers on that. So in AQPI, one of the major emphasis is on more emphasis on model compared to the Dallas-Fort Worth project. Dallas-Fort Worth project was more of civil defense in megacity for transportation and airport. Here it's more of water resource management, and so we do have assimilation into models. Yes. The short answer is yes.
Okay. Anyway,
One thing I want to address.
Any other? Yeah, please.
Yeah, so the thing which you're talking about, the combining the hydraulic model and street models. So we also tried in India at two places, Mumbai and Chennai, along with various other like IIT Mumbai and IIT Chennai. So we have come up with it, and that is being under trial also for the last couple of years. So that also we have made some.
Chennai and Mumbai, we have made a flows. There is a atmospheric, and of course we are not connected to storm surge, but we have connected atmospheric and river and path drainage system.
So Professor, I have a question. It's a bit different from the precipitation and the radar, but you mentioned about the system operation, how you can best optimize the system so as to get the best response. So I worked on a project on disaster management in Mumbai, wherein the idea was to predict the response time for the fire brigade to reach the emergency locations during any kind of emergencies. So my question is, what is the best response time? Like, in what terms are you evaluating the response time in this case?
Yeah, so here in terms of getting the response from people, sometimes you ask people to evacuate, they refuse to evacuate. And so in Dallas-Fort Worth, one of the things we did was like a hail index, because it hails a lot. And so we developed the time hail integration index and showed the damage pattern. So that's for civil defense people to respond. But then we have this, what is called as reverse 911, where you have flooding starting to happen. Then the model says flooding is imminent. Then we send information to people and ask them to evacuate. In the evacuation, if you tell them, there is some study done with sociologists. You tell them you have 30 minutes. Then people want to prepare a baby formula, they want to finish their phone call, this, that, everything. They think, oh, we have 30 minutes to do this thing. You tell them you have to get out in 5 minutes, they drop everything and go. So people studied this type of people's behavioral response and try to factor it into that. So for that, you saw one of the main statements made was false alarm. Enormous effect has to be brought in to reduce the false alarm. If the false alarm doesn't come down, next time you predict accurately, nobody listens to you. That's so. People are putting more effort into bringing down false alarm at the cost of missing the detection. It suddenly turned reverse. When I was younger, detecting the event was more important than it's better to overwarn instead of underwarn. Now, because of this too much information, you miss an event, they will give forecast, nothing will happen.
No, but in your case, what is the amount of false alarm rate you have?
So our case,
because
we are
that's
not
very
doing.
important. Like we do in military, we have very stringent false alarm.
Yeah, their false alarm is life and death.
Yeah.
So here in this case of Dallas-Fort Worth, with the current infrastructure, he will know the index. F0 tornadoes are not detected. So, and because they are so short-lived,
it's our cloud burst.
And
density is high.
And the thing is, its time existence is less than 5 minutes. It will create damage. And we did very well with the F0. And so we improved reduced the false alarm of F0s. Because it comes
correct one kind of some of the radar parameters. What will be the beam weight? What is the kind of dwell time? All that it will become very significantly dictated by the radar parameters. Design parameters. They are exclusive to design parameters.
I think he's trying to say something.
I was going to say that we have reached T zero at this point. So it's 7:30 and we reached the hour. So this conversation obviously clearly generated a lot of interest, and we can continue, but we can maybe officially first say a big thank you to Professor Chandrasekhar for coming and giving us this enlightening talk, and then those who have to retreat can do so. Yeah.
The most important thing is that I want our Dr. Ravi Chandran and Professor Chandrasekhar and your department. I think we should start getting into the collaborative mode, so that we can at least 1 or 2 pilot projects we can run through. We have done a couple of projects for US and doing Korea and Japan and all that. So why not we get facilitated through?
Yeah, and that we can do that.
So I request you to.
I think our IITM already in collaboration with this one, but not academic.
Formalize PG.
Academic,
formalize PG.
Especially in hill area.
Particularly select some of the hill areas, vulnerable hotspots as we call them. Let us
the cloud burst, the fresh floods.
let us get 1 or 2 projects along with this, and let us bring the industry in that, so that those radars can be produced here.
Yeah. Yes. Absolutely.
Yeah. Thank you very much.
Thank you so much.
Thank you so much, Professor. Thank you very much.
Yeah, I have not 3 times on.
You want to take a group photo?
I think it is required.
Why don't we take a group photo?
Aye.
We have seen.
Actually, maybe.
Very much.
We'll miss everybody online.